Over to you, Sandhya.
Good morning and a very warm welcome to one and all present here. Myself, Sandhya, Assistant Professor, Department of Pharmaceutics. I feel proud to introduce one of the person of this online FTP, Dr. Gopinath Haldar sir. He is currently working as professor in NIT Durgapur. He has completed his PhD and MTech from Jadavpur University, Kolkata. He has 21 years of research experience and 18 years of teaching experience. His area of research interest was wastewater treatment, biosorption, FICO and microbial remediation, safe disposal, solid waste management, low density polyethylene, high density polyethylene plastic management, biodegradable polymer synthesis, safe disposal, biofertilizer formulation and development from solid waste. Sir has published 150 research articles in peer-reviewed SCI journals. Sir has authorized a textbook titled Introduction to Chemical Engineering Thermodynamics. He has guided 12 PhD scholars and 6 scholars are working under him. Sir has been awarded with Fast Track Young Scientist Project Award by DST Government of India. He has handled 10 funded research projects from DST and DBT. He has served as an expert member for Faculty and Research Fellow Selection Committee. He is a member of Royal Society of Chemistry London, American Society of Engineers USA, Indian Institute for Chemical Engineers India, Institution of Engineers India. Sir, you are really an inspiration to all of us. With the honor, I would like to welcome you once again to the
welcome, sir. Yeah.
Thank you. And I think I am audible to all of you.
Yes, sir.
Yeah. So it's a very good morning to all of you present over here. Thank you so much, Dr. Sandhya, for introducing me so nicely. And I am expressing my sincere indebtedness to the organizers, faculty members of the Department of Pharmaceutics, Vishnu Institute of Pharmaceutical Education and Research, Medak, Telangana, especially the coordinator, Dr. K. Banita, Professor and Head, Department of Pharmaceutics, VIPER, and Dr. A. Ramesh, Principal, VIPER, and Dr. Wayne Tiwari, Principal Scientist, iCare, IERI, New Delhi, for giving me an opportunity to share my thoughts in sensitizing the young researchers and faculty members from different academia, R&D institutions, and industries on the 5-day online faculty development program entitled Recent Advances in Science and Technology Innovations through video conferencing meeting via Zoom and YouTube platform. I heartily welcome all the distinguished delegates and participants coming from various corners of the country, of our country, India, and other countries also, from different academic institutes, research laboratories, and industries to this 5-day program. I'm very sure that this series of webinar will be very, very productive and informative to the August audience for execution of their research and technology implementation in the new direction. So now let me just share this just for a while. Please excuse me for sharing this PPT. Is it visible to all of you, please? Kindly.
Yes, sir. Yes, sir. It is.
Yeah, it's visible. Okay. So now I am going to deliver a talk and my small experience, if it is possible to be effective for the participants, then really I'll be very happy and we really enjoy delivering this talk. And I'm going to deliver this talk considering one of the piece of my research assignments, where I would like to cover a periphery of the common interest. Biosubstitute eradication of ibuprofen from contaminated aqueous media using biochar. See, we are very familiar with this ibuprofen. This is a non-steroidal anti-inflammatory drug, and this is also being treated as a very active micropollutant in the pharmaceutical direction, because there are so many pharmaceutical active compounds, those who are presently being considered to be the active contaminants also, because those who are creating the contamination in the surface water and the groundwater also, those who are getting relief from the different pharmaceutical outlets, medicines, and pharmaceutical industries and different hospitals. So today I'll be just delivering the process by which this water, how it can be contamination free and how it can eradicate these ibuprofen, these pharmaceutical active compounds and micropollutant from aqueous media. So this is just, let us have a look onto the outlines of this presentation. Just it can be broadly categorized into the 5 segments. This is one, the interaction, the investigation and the findings, and the analysis of the findings, and finally the conclusion. What is ibuprofen? So you see, being in a profession of teaching, so always I used to start from the very basic. Whenever I used to deliver a lecture for a specific subjects to my students. So here also, first of all, we need to know what is ibuprofen and what is its demerits, what is its drawbacks basically in using. So this ibuprofen, we are very familiar with these antibiotics. We are very familiar with these anti-inflammatory drugs. So the name of ibuprofen, in the sense of chemistry, basically if we consider these 3 different groups, okay, so these 3 different functional groups, ibu from isobutyl, pro from propionic acid, and fen from phenyl. Therefore, considering these 3 functional groups, after amalgamation, this group has been jointly summarized as this name, in the name of ibuprofen, which is also known as 2,4-isobutyl phenyl propionic acid. And this ibuprofen, this is one of such non-steroidal anti-inflammatory drugs, which is extensively used as the painkillers or pain relievers, what we generally use and consume in our daily life for the treatment of inflammatory disorders as per the prescription of the doctors. And presently, this tendency has increased in such a way that this is really alarming, because I'll be giving some statistics and some data that I will before you to present, where you can really notice this alarming figure of the consumption pattern in our country and other country also. IVP has moderate water solubility and hydrophobicity, along with a high mobility in the aquatic environment. Antibiotic consumption rate, this is increased. I have got the information for different other countries, but particularly for our country, this is really a very matter of concern, as this 8.2 to 13.6 defined daily doses in billions per day in our country, and that has been increased to the tune of 63%. So this is really an alarming figure. I'll be giving you more information regarding the consumptions of this IVP, where you can see that the IVP consumption is gradually increasing day by day, and this is one of the greatest concerns as a cause to the contamination of these waters, what we are basically getting from the different sources, and that makes it unfit absolutely for the human consumption. So our main concern is to treat this water contaminated already by these pharmaceuticals active compounds. Now, before that, I would like to present you some very important information. So here you see, just let us take a look on this consumption pattern of pharmaceuticals in the world. And you can see that there are a number of pharmaceuticals, number of antibiotics, number of NSAIDs, non-steroidal drugs. So where antibiotic and the other compounds, pharmaceutical active compounds that are getting consumed daily life in their life, it's okay, fine. Here, ibuprofen, this is, you see, it's about, this is really a good, this is 12% as it accounts for the contribution to this consumption pattern, and as compared to the other pharmaceutical compounds, I mean, percentage is huge. So this is really alarming that these uh, ibuprofen consumption, and if it is the root cause of the water contamination through the pharmaceutical outlets, so then definitely we, the researchers, we chemists, we engineers, so we need to think about, we have to, we the environmentalists, we have to think about the contamination, how this is to be free from this contamination in the aqueous media. Now let us have a look on the basic properties of this ibuprofen. The chemical formula is C13H18O2, and this IPAC name that I have already hinted about, this 4,2-methyl propyl phenyl propionic acid, because this ibuprofen, this is isobutyl propionic and phenyl compounds, okay, and the structure is there, and molecular weight is 206.29, and their use and pK, that means this acid dissociation constant, that has been also given. Now, what is the negative impacts, and what is our main concern basically? Ibuprofen that you are using, and what is the negative impacts on the human beings, on the other animal kingdoms also. So here, just you can see that this metabolizes as hydroxyl and carboxy-ibuprofen in aqueous solutions, has an accumulative effect and results in great changes in the ecosystems. And one specific form which is very, very deteriorating, very, very deleterious, because this 4-isobutyl acidophenol is the toxic degradation product of IVP and produces adverse effects on the central nervous system. It disorders the central nervous systems, and there are, you can see at the left hand side, at the right hand side of this, what are the side effects of ibuprofen on consumption, where there's nausea, diarrhea, stomach pain, stomach ulcers, and in most of the important organs where it can create the huge, I mean, anxious diseases. Okay, these asthma attacks, kidney damage, allergies, blood vision. So these ibuprofen concentration, if we can consider, this is in very minute quantities and very trace concentration that is available in water. But these, even at the trace concentration or very low level of concentration, it may cause a huge problem. It may cause huge effective diseases on consumption of water, where this is already available through the different pharmaceutical outlets and the pharmaceutical industries and medical outlets also. Just according to the US and European regulatory guidance, current pharmaceuticals are subjected to the standard acute toxicity test when the concentration of the active ingredient in effluent exceeds 1 microgram per liter and 10 microgram per liter. But I am telling you this information because I am presently involved in this direction for a couple of years, where these concentration that goes on increasing day by day, because this consumption of this IVP that also goes on increasing, and this variation, this is differently involved in different countries and different pharmaceutical outlets and different natures of water also, because it's subject to the availability of the different pharmaceutical outlets and the consumption pattern in day by day. Now, sources of pharmaceutical wastewater. So this wastewater, how this is getting contaminated and how these pharmaceutical active compounds or the micropollutants that are responsible for creating the pollutions. Here, just let us have a look into these. So these pharmaceutical compounds, not I'm talking about this ibuprofen, ciprofloxacin, norfloxacin, ranitidine hydrochloride, then the meloxicam, naproxen, diclofenac, uh, ketorolac. So these are the different kinds of these pharmaceutical compounds. These are observed to be present in their acute concentration in what bodies. So here you see these human drugs. So what generally prescribed for the humans as medicines. So through these human drugs, so that are also one of the important routes by which this is getting contaminated, and this is getting basically mixed with this water, and where these human drugs on consumptions through excretion and urine. So this is being released to the sewage and the sewage treatment plant, and where once it is mixed and contaminated, uh, this is being also made available in drinking water, because we do not know where this is present and how this trace concentration of this micropollutants and pharmaceutical active compounds present in the water. And finally, you see how serious the issue is, and this is also we are consuming. Okay, so this is necessarily to be treated by the environmentally benign and very cost effective and very energy appling technology, so that this water or the what bodies or aqua media that can be treated well, and there will be no contamination, and the man and the human beings, they can consume it very safely. Now the second is hospital waste. So hospital waste, where these pharmaceutical compounds that are used, and where from these waste disposals and then landfill sites, soils, and see through the seas of these foods, where this is getting mixed with the groundwater, and this groundwater, that is one of the parts that is also mixed with this, and what the component of this drinking water also, and again this human, this is consuming this drinking water by mistakes, or unknowingly or unintentionally. So this concentration and this trace concentration of IVP that is present in this water. Pharmaceutical industry waste. So the pharmaceutical industrial outlet, where the pharmaceutics or the pharmaceuticals basically are getting manufactured. So where from this is moving on to the different waste disposal, again this landfill site, soil and groundwater. Finally, this is getting released to the groundwater, and again there is a chance of mixing with this drinking water, and finally we are consuming this. Now, water pollution via ibuprofen, basically the same thing, but specifically since we are putting a concentration of ibuprofen, so here this ibuprofen that is following the same routes to contaminate this water and to mix with this water, and finally we are getting this water in our daily lives by mistake. Okay, so this water is to be necessarily treated by the effective technology and the environmentally benign technology, so that there will be no chance or no scope of secondary pollution to the groundwater through percolation, and this treatment will be very cost effective and implementive, so that we can get the contamination free water from these different pharmaceutical active compounds. Now this but the motivation that basically to compels us to do this kind of research. So here you see, just let us have a look at this different figure. Just I am segmented these three different components: the availability, prediction, regions, and initiatives. And where you can see that just this is the notation figure. You see, the entire water content around this planet, if it is broadly categorized into two different components or two different classes, you see the salt water, this is to the tune of 97%, and fresh water, this is to the tune of 3%. Now you see this fresh water 3%, this is only available as that we are consuming in different ways and different patterns. So now these water, if this is getting contaminated by means of presence of different components like these pharmaceutical active compounds, like heavy metals, like organic pollutants, like inorganic pollutants, like TDS, like BOD, like COD, oil and grease, and the different components, if it creates the pollution, so then it will really be a difficult situation by them to get this water in a fresh quantities. Now the prediction. So here you can see this. Just let us take a look, a very noticeable figure where you see the over 2 billion people experiencing the high water stress as per the reports, UN reports, and by 2040. 1 out of 4 of the world's children under 18 will be under extremely high water stress. So this is the report as per the UNICEF 2017. So now what the engineers we should do, that what the chemists that we should do, and what the chemical engineers people, the pharmaceutical engineers, they should do it. So here, and you see the regions. What are the regions? If we can consider the regions, so these are unmanageable population growth, globalization and industrialization, environmental degradation, and excessive use or wastage of water. So definitely these are very, very common causes and common regions, so that we know and that we must be aware of. Now, what are the initiatives that we must take into account for the use of this fresh water, and for not to waste this water in such a way that water can be useful and water can be consumed, or water can be used in different ways in a judicious manner. So here there are the different initiatives that have been taken by the different chemists, engineers, and chemical engineer people, environmental engineers. Now here my approach is, apart from this water recycling, water harvesting, improving sewage systems, smart agriculture, the water decontamination. That means water, it must be free from contamination. So these contaminants, if we can treat it properly in the aqueous medium, so then this water can be fit for the human consumption, it can be fit for the agricultural purposes, subject to the presence of the micropollutants, subject to the presence of the contaminants in the aqueous medium. Now the treatment processes. Without taking much time, I'm going to the detail of the different treatment processes what presently the research community they generally used to consider for treating this water. Here you see this photocatalytic photodegradation, micro-extraction, the membrane separation. So membrane separation that can be categorized into different classes, where there's ultrafiltration, nanofiltration, reverse osmosis, fast filtration, and this electrochemical oxidation, adsorption, microbial remediation, I mean with the help of these different microorganisms like the different bacteria. So that can be also a useful tool for treating this water through the bioaccumulation, biodegradation, and biosorption. And the phytoremediation and phycoremediation, these are also the bioremediation processes by which this water is used to be treated for the removal of the different contaminants and micropollutants from the aqueous bodies. Now this adsorption, this is a very, very common separation phenomena, separation process, and where the adsorption that can be categorized into two different classes. One is physisorption and another one is chemisorption process. That means this physisorption process, when the adsorption process occurs due to the weak van der Waals forces of attraction, and the chemisorption where the adsorption is responsible for the strong chemical bonding of the components, what you are considering for its absorption onto the adsorbent materials. Basically, the adsorption process employs the adsorbent and adsorbate, the pair that is employed for the adsorption process to occur. Now, the precedence of adsorption process. So it has been already noticed that there are several processes on which presently the research community they are working out for the separation of the different contaminants and micropollutants, or for the treatment of wastewater by different processes like ion exchange process, I mean coagulation, precipitation, photocatalytic degradation, membrane separation like cross filtration, nanofiltration, reverse osmosis, then this biosorption, phytoremediation, microbial remediations. Now, why you are considering this adsorption process? Here I can share with you all that this biosorption process, that is one of the components of this adsorption process, where the sorption process is mainly contrived on the production of these sorbent materials developed or derived from the biomasses available plenty in the nature. So this abundantly available biomass. So what we are considering as the precursor material for the preparation of this biosolvent based on this biosorption process occurs to make the process environmentally cost effective and benign in nature. So now this adsorption process, where we are considering this adsorption process over other, what is the reason, and what is the reason behind the selection of this process over the others? So here is, you see there are some positive factors or positive points that you can take into account for considering this adsorption process over others. So here it is very observable that this operation concerned with this adsorption process to take place. This is very easy and it's proved to be a very feasible technology at larger scale. And here the removal efficiency is excellent, and the sludge generation. This is also a very important thing, that sludge generation, you see, adsorption and other different processes by which the separation of the different contaminants or pollutants from the aqua media has been possible to a greater extent. This is fine. But the challenge is the disposal. I mean, the safe disposal of these treated, safe disposal of these secondary pollutants, or the safe disposal of the sludge what we are getting after the treatment is over. For example, I can tell you this biochar process where this biosolvent materials, ready solvent materials by which this water is getting treated, and the 98%, 99% and the same percent removal that is possible. But after removing these spent adsorbent materials, where it can be disposed of into the environment to avoid the secondary pollution to the population, because it can get mixed again with the water, which may be the main cause of this pollution, water pollution. So we have to think about the safe disposal of these spent adsorbent materials, or the materials what are generally employed for the treatment of this water through the different contrivances or different technologies. So here, this sludge generation, this is one of the very important and positive advantages, cost competitive, and the scope of potential use of the solvent materials. And the solvent materials what we are preparing basically, or being prepared by the different researchers, if we can add up the effective process of solvent preparation, then this is really cost effective and very low cost, and it is very effective in sorbing and removing the pollutants from the wastewater. And this is having the low energy requirement and the less maintenance. So these are the few advantages so that are possessed by the the adsorption process, and that's why this process has been employed for the treatment of wastewater. And very important information that I'd like to share with you all, that you see all these domestic uh, water purification unit or water filtration unit what we are having in our daily life, and we are consuming this water from this unit after filtration. In every purification unit and every filtration unit, where appreciable amount of water that gets treated by adsorbent materials and that are present in the filter, and after every 3 months or after every 6 months or after a normal frequency or a regular frequency, we need to get this refilled, okay, with the help of these adsorbent materials. And you may have seen that this is mostly the activated carbon, and this is refilled, I mean this cartridge is refilled with this adsorbent materials. So adsorption process is very, very important process and cost effective process in expulsion of the different micropollutants from water, and that we can experience in our daily life also through this different costly or low cost filter or water purification unit what we are using in our daily life. Now, this is the graphical abstract. What I'm telling, this is a graphical abstract because this is a glimpse what I basically used to consider here, on which I'm going to deliver this. Just a specific or a sample research on which the findings that will be discussed and analyzed. But this is not the only domain, or this is not the only precursors or only materials, so that we are, apart from these, any other materials, how it can be prepared, other adsorbents, other adsorbate, how it can be considered, so that I'll be also discussing. But this is just the base or the reference that we can consider here. So here you see this biochar. So that has been considered for the softive eradication of this ibuprofen, the micropollutant, I mean pharmaceutically active micropollutant. And here this is this tamarind sheet that has been used as the precursor materials. Apart from these tamarind sheets, actually I have been involved in this preparation of indigenous development of adsorbent materials over the last 20 years, and where I have used many precursors which are abundantly available in the nature. Plenty of biomasses which are available in the nature, which are waste biomass, and that are having huge capability in terms of their different characteristics, what we generally consider for the suitability of an adsorbent materials. And the success of an adsorption process largely depends upon the performance of an adsorbent material. So if we can prepare this adsorbent material based on the proper process and considering the parametric condition, then it will be a very effective tool for the successful elimination of the different micropollutants or contaminants from aqueous media. Now here just a sample process that has been considered, but I will be considering the other materials also, so how it can be prepared and how it can be activated. Just this graphical abstract is indicating the different small segments what I am going to cover. This tamarind seeds that has been considered as the precursor materials and that has been crushed, and this biochars, biosorbent that have been prepared, and this is activated with the help of these chemicals agents. But the physical activation where no need of introducing these chemical materials, where you can introduce these superheated carbon dioxide or superheated steam, by which it can be physically activated at certain temperature, I mean the suitable temperature and pressure that I'll be discussing. And here this adsorption process has been taking place to eradicate these components. And here the kinetics, isotherm, these are very important peripheral studies, so that we need to do to substantiate the technical meanings and justification of this process. This kinetics, isotherms, thermodynamics, cost estimation, desorption study, because this is this regeneration of the spent adsorbent material. This is very effective in substantiating the success of this process, because if it is having a huge regeneration capability after a good number of cycles, then this process will be very cost effective, and the materials that can be also used for a repeated number of cycles, considering the dimensions or the dimensional retentivity of the materials. And this RSM that has been basically considered here for the optimization of the process parameters of this soft tip removal. Now here the selection criteria of promising precursor for biochar. So first of all, what is biochar? So that we need to know first. Biochar is nothing but carbonized char or carbonized matter or carbonaceous matter derived from the biomasses with the help of pyrolysis or with the help of carbonization process, where this temperature and time are the major or the prominent factors, so that we need to consider for the carbonization, through which this carbonized char is derived from the biomass. So biochar is well defined by the carbonized char derived from the biomasses with the help of pyrolysis or carbonization, subject to the specific or the suitable temperature. Now this biochar, this is used here because this biochar that has been aimed to be produced from this waste materials, and where we have checked that the surface area and micropore volume and the total pore volume, adsorption capacity, which are the major characteristics that should be possessed by a suitable biosorbent materials, and that are also observed to be really significant. And that's why we use this biochar materials. And not only me, you see biochar, this is the material that has been extensively used by the different researchers in around the world, where biochar this is having a capability of absorbing a good and huge amount of sorbate materials, sorbate which is available in the solution where the micropollutants or the contaminants are there. Now, what is the selection criteria, and why we should consider this precursor material, and what are the different conditions or different factors or the criteria that we should consider for the selection of promising precursor materials for biochar development? It should be waste material. You see, if we can get this waste material from the nature, so then definitely we have to think, we have to choose, we have to apt in such materials that which is having certain capability of absorbing these ions or molecules from this sorbate solution. So if it is waste material, then the process will be definitely the cost effective, because it will not attract that much of cost high hardness value. Hardness value, this is very important thing, because if it is hard and if its hardness is good, then what will happen? It can be used for a repeated number of cycles where it will retain its dimension for a number of cycles. Okay, so its dimensions is a very important thing. I mean, after successive cycles, its dimension should remain same, and the dimensional retentivity, that is also an important factor. Excellent adsorption capacity. Definitely, as this term itself is a self-explanatory, that means its capacity of adsorption of the ions or the molecules or atoms, if it is good. So definitely, we need to consider this kind of precursor materials, and the larger fixed carbon content, easily available, low cost, highly microporous structures. So these are the different factors that you can consider for the biochar. Now, how can we know about the different criteria? Actually, we need to go through the different series of tests by which you can get this, whether this, suppose this uh, fixed carbon content. So if we want to know the quantity of the fixed carbon or the fixed carbon content of this precursor material, so we have to consider the proximate analysis, where we need to put through the series of, processes by which we can get the information about the fixed carbon content, volatile matter content, moisture content, and the ash content. And where the fixed carbon content will be the major concern, because higher the carbon quantity and the higher will be the possibility of active sites of the surface and the microporous structures and the surface textures to be around the surface on the adjacent materials. So these are the major criteria that you can consider for the selection of a promising precursor. Biochar preparation. Here you see this tamarind seeds, what has been considered here, particularly for this case, where the tamarind seeds were washed and then dried in water even at 80 degrees centigrade to remove these impurities and the moistures. Okay, and then it is dried, and the dried seeds were crushed and screened at 125 microns, and then this crushed sample were carbonized at 500 degrees centigrade and then choked with ACPO4 solution for 24 hours, and then this is dried activated carbons or these activated biochar. Now you see these activated biochar that has been produced through the different different processes. First it was dried, then to remove this moisture content, and then it was size reduced, and then it was screened. And the H2PO4 solution that has been used as the chemical activating agent. Actually, here I would like to mention one thing: the activation of carbonized char, the carbonized matter, which when converted from the biomass on carbonization or pyrolysis, that can be activated by means of the two broad processes. One is physical activation, another one is chemical activation. Now the physical activations, where the physical activating agent is the superheated steam, or superheated carbon dioxide, superheated gas, any other gas, okay, and where this pressure and the temperature and time, these are the three factors that we generally consider and that we generally take into account for the effective activation to develop the sufficient or appreciable micropores and to enhance the surface area. This is also the surface modification process, okay. And the chemical activation, where the chemical activating agent that we generally use are H3PO4, the orthophosphoric acid, sulfuric acid, sodium hydroxide, potassium hydroxide. So these are even the zinc hydroxide, given different kinds of chemical agents that we generally use for the activation of this carbonized char as activating agent, okay, to develop the micropores appreciably and to enhance the surface area. This is also one of the processes of surface modification. Now, here I'll be discussing, apart from this tamarind seed based activated biochar, here this activated biochar, it may be of different shapes. Here this activated granular biochar. So just this process that has been mentioned here, the physical process, this crushing, suppose the coconut shells that you have collected from the market, that you have collected from the garden, you have collected from the different places, local places, okay. So then these are the series of processes or steps that we can undertake for the conversion into biochar. The crushing, then washing, then drying, the carbonization, then size reduction, then the steam activation. That means the superheated steam that will be passed through this Mapur furnace, where this temperature and time that will be maintained and the pressure that will be also maintained, 1.5 to 2 kg per centimeter square, and this time and temperature. You know, this time temperature, this is varying for different precursor. It varies from precursor to precursor. And now the question is, how should you decide this temperature? Actually, this temperature of carbonization that is generally decided by the thermogravimetric analysis, where if we consider the analysis of this sample, then we can see that the temperature at which there will be no further mass loss with respect to the temperature if the process proceeds or if the process is allowed further. So this temperature is very decisive, and that you can get from the thermogravimetric analysis, where from you can see that this temperature that can enable these materials to be developed into activated biochar, where it will be possessing appreciable micropores and enhanced surface area. Now here you see this is another form, another step. This is pellet. So here this crushing, drying, carbonization, mixing, all the basic 4 steps, these are basically same. Now this pelletization, where this pellet will be formed into, it will be pelletized with the help of binder, okay, and then it will be dried, and this steam activation, where again the physical activating agent, the steam that has been used here to enhance the surface area and develop the pores. Now this is one more process. Here you see we have amalgamated these 2 different kind of agents. I mean the physical activating agent and chemical activating agent, so that we have used both in the activation. Sometimes it is experimentally observed that these micropores, so that may be developed to a huge extent and surface area also. Okay, so if this is performed following the 2 different kinds of activation, like physical activation and chemical activation both. So here you can see this after crushing and drying, then the carbonization unit, and it moves on to the size reduction, and then the steam activation unit. And after steam activation, this is activated with the help of chemical agent, and where this is chemically activated, and that's why this is physico-chemically activated biochar. Okay, and then this is to be neutralized, because if we use alkali or acid as basically the activating agent, so that will be basically removed through the process by which these ions will be neutralized, because we do not know what kind of micropollutants or what kind of contaminants that we are basically considering to be removed from this adjuvant materials, and how it will affect the process, and how there will be the ionic interactions or inter-ionic activities. So that's why on neutralization process, these materials finally we are getting this is basically the physico-chemically activated biochar. Now the preparation of these solutions. So the adjuvant materials that is ready, that means the biochar that is ready, and that has been produced from these tamarind seeds after the different parametric conditions considered in this process. Now the sorbate solution, this is IBP solution, and you see here the stock solutions or the adsorbate solution that has been prepared, okay, and the different parametric conditions, this pH, this removal process, where this pH, sorbent doses, initial IBP concentration, and the temperature, agitation speed, and the contact time. These are the 6 parameters or the 6 factors that we have considered here to check the influence of these individual parameters on the removal of this IBP. And here you see this Q, the C0 minus CF by M. Here the initial concentration and the final concentration, okay, and this V, the value, okay. So where from we are getting this removal percentage and the quantity of this IBP that are getting eradicated, okay, at equilibrium conditions, so that we can know from using this UV spectrophotometer to measure the concentration. So UV spectrophotometer, so that we have used here to measure the concentration of this IBP solution. Because you see, initially, suppose this concentration that was present initially, so if it is targeted to be reduced after this treatment, so how much it was reduced? How can you know that? So that has been examined with the help of UV spectrophotometer by measuring the concentration of this resulting solution. Now the characterization of this biochar. So here these are the four parameters that we have basically considered, four instruments that we have considered basically by which the biochar has been characterized. Proximate analysis. So proximate analysis, this is the analysis that we generally conduct in the energy laboratory or in the fuel laboratory for solid fuels. So here this biochar, this is the carbonaceous char developed from the biomasses that has been undergo this proximate analysis to know the moisture content, volatile matter, fixed carbon content, and the ash content. Okay, and here this process also consider the parametric condition at every steps. For the first, we go for the removal of this moisture content, and then the volatile matter content, then the ash content. Okay, and then after removing this moisture, volatile matter, and ash, so finally, what the amount is, that is basically we used to get after summation of these three amounts, subtracting from 100. Okay, that is basically the fixed carbon content, and that we take help of proximate analysis by which we get the fixed carbon content, and that is our main concern. Okay, FTIR that has been used to predict the functional group of these adsorbent materials and the solutions also. And here same, the scanning electron microscopy that you have used here to determine or to check the surface texture and the surface property of this material. So whether this is even or the surface is even or surface is odd, or okay, and whether these cylindrical pores are formed and whether this is blocked or not. Okay, so that kind of information that you can get from this, and EDX where the constituent elements and their composition, so that you can get from this analysis EDX. Okay, so here just one by one I'm going to be very quickly. Proximate analysis. Here you see this adsorbent before carbonization and after carbonization, and we are basically observing these four parameters: moisture, ash, volatile matter, fixed carbon. Before carbonization, that means the precursor materials what you are considering for the development of this sorbent material, so that will be also undergoing the proximate analysis, wherefore we can get to know about the percentage of these four components: moisture, ash, volatile matter, and fixed carbon, and after carbonizations how much it is and what the change is. Okay, so that can be observed after carbonization process if it again allowed to undergo the proximate analysis. And where if you can see that this is really noticeable that this volatile matter what is present before carbonization, this is 71.21%, and after carbonization this is 13.48, and you see on the other side where the 70.98, that is the fixed carbon content, this is a huge amount what was initially before carbonization 20.02. Yes, this is with obvious reason because this volatile matter is lost, and this amount is really a low amount after carbonization, and that has enabled this matter to be converted into the carbonaceous matter, and that's why this fixed carbon content that goes on increasing. FTIR. So here you see these two different kinds of adsorbent materials, I mean the biosorbent or biochars. Okay, so what was before and after, where we have seen that these different functional groups, these alcohol groups, phenolic groups, hydroxyl group, amine groups at different wave numbers that we have observed, and after that this band was shifted to that after adsorption process when these materials was used. That means the biochar materials what was taken part in the adsorption process for the removal of this IVP, and where this is again analyzed, and where these carboxylic group, alcohol group, and carboxyl bond, so that were also observed with the help of this shifting of these bands with respect to the wave numbers that we have observed here. Same, so here this is very clearly visible that it has number of apertures, number of pores, micropores, Actually, these pores that are categorized into three different kinds: micropores, mesopores, and macropores. So macropores are available, mesopores are available, micropores are available. But here, these micropores, these are very desirable, and this micropores are in huge quantities, and that will be basically playing a dominant role in absorbing the ions from the absorbed solution. On the contrary, where you can see that this TCAB after adsorption, where the pores that are observed to be choked or blocked on absorbing the ions in the adsorption process. EDX analysis, where you can see these elemental constituents of this TCAB and weight percentage that are given, the CO, NAP, and these are the four peaks that you are observing in the figure, where this carbon, oxygen, sodium, and P, this phosphorus. Basically, this is the component that is being introduced here on introducing this orthophosphoric acid used as the chemical activating agents. And where you can see these if we just check the weight percentage, and here it varies. No, so this TCAB after and before adsorption, this is very clearly visible from this figure and the data that, so this P, that means this is, I mean, the components that are highly adsorbed onto the active sites of the surfaces of the adsorbent materials, and that are reflected on the result in the EDX. Now these results and discussions, so what we have got basically. So here the 6 factors that you have considered in the math study. Actually, you see these 6 factors, why should you consider, and how do you decide these factors? Actually, the adsorption process, so that depends on the different parameters for resulting in effective removal of the contaminants or the pollutants what you are targeting. So here, this pH concentration, this is a batch process where it can enable this result to be very effective, so that we do not know. So that's why one parameter that is to be varied, keeping other parameter constant. Then we can only be in a position to say the specific ranges of these parameters which has been varied, keeping the other parameters constant. So here you see, so this is the results that we have observed here, where you can see that this pH, where you can see this pH at pH 2, that means the resulting results that have been noted here, the pH, that means at 2 pH, where the maximum removal is 72.69%. So this is not the final result, I mean the 72.69%. Just you can check, you see this. This is the parameter that we have considered, and at which particular optimized conditions it will give the better results. So that has been basically found out with the help of these specific parameters on variation, keeping other parameters constant. Now the initial concentration, where you see this 15 mg per L, the maximum removal percentage is 76.23. Now there will be an obvious question that why this pH, the 2 pH, that means the acidic pH, where it has shown the maximum results, and if it is so, then what will happen if the solution is considered, and if the technology is considered to be implemented in the commercial side, and because this environment is acidic? Actually, you see, there will be no issue, there will be no problem. This result is basically observable and maximum achievable on pH 2, because if we can observe this value, the acid dissociation constant force, so 4.39. So then what will happen? At pH 2, removal percentage was 72.69%. When pH was increased from 2 to 7, it was found that the removal percentage that decreased from 72.69% to 40.14%. Yeah, this is due to the IVP's pKa value of 4.9. So that I have already shown you in the common properties of this ibuprofen. And here this above pH IVP residues in anionic form, and the concentration of which is henceforth indicated by the mole percentage. In anionic form, it moles increases with pH, and since at pH 4 and 7, IVP mole percent, this is basically in maximum quantities, and these protons of ibuprofen quickly it bind with the hydrogen ions and get adsorbed when the pH value is low. So these functional groups separated when the effect of pH varies as the exterior chemistry of the solvent changes. So that's why these value, this is available at 2, and this is also observable in many other cases also, where it gets the maximum result at acidic value, or sometimes it is at neutral, sometimes it is at alkalinic value, depending upon the scale of this pH. Now this initial concentration, where this initial concentration, where this is see that the 15 mg per L, where at the maximum removal, the 76.23% has been achieved. And after, I mean, as the process proceeds and as the concentration that goes on increasing, uh, here the removal percentage that is decreased. Basically, the active sites which are responsible for the absorption of these ions, so that are going to be saturated as the process proceeds. And this concentration, that means the IBP concentration, then when it goes on, increasing. So it basically the removal percentage that declines, since the excess IBP molecules make the overlapping of these active sites of the adsorbent inaccessible. Okay, so same thing, similar kind of trend that you can observe also in case of adsorbent doses, where it goes on increasing and the percentage removal that will be decreasing with respect to the increase in adsorbent dose. The same thing that you can see here also. And agitation speed, so here you see agitation speed, what has been observed here, the 160 rpm, that is the maximum optimized rpm, where you can get this 88.77% removal efficiency. Okay, actually this is depending upon the nature of the process, whether this is physisorption process or chemisorption process. If it is physisorption process, then of course all of you know that the physisorption process, that is very much concerned with the van der Waals weak, forces of attraction. Okay, but and this is weak, and chemisorption process, this is comparatively stronger, okay, than this process. And where agitation means the styrene feed, so the rpm, if it goes on increasing, then what will happen? Then it will basically detach these ions or molecules from its active sites around to the surface of the adsorbent materials. So up to a certain agitation, it will show the maximum removal percentage. But after that, when these agitation perturbs the intraionic interaction, then it will show in declining the removal percentage. Influence of temperature and time, and where you can see that the resulting temperature and removal percentage is 35%. 35 degrees centigrade is the effective optimized temperature at which the maximum removal was 95.44%. And here the contact time also, so that time that we have considered on elapsing 3 hours of the experimentation, the maximum removal percentage is 89.58%. So here you can see that the every individual parameter on its variation, the maximum removal, how much it was observed, keeping other parameters constant. Okay, and that has been considered as the set of optimized best parametric condition to achieve the best result on manual optimization, rather the software optimization or the software or any tool what we generally use nowadays for the optimization of the process parameters. And here you see the another approach that optimal that parameters what we have considered on manual optimization, that set of parametric conditions that we have achieved, and in parallel we have used also here the software tool to check whether this condition is right or not by checking or by plotting this actual versus predicted path. Where the central composite design, this approach of response surface methodology that has been used here to find out the best parametric optimization conditions. And here you can see there's 1, 2, 3, 4, the 4 parameters that you have considered. And for 4 parameters, the 30 number of experimental observations will be designed considering the experimental matrix. And considering these experimental matrix, we have to perform these experiments and we have to check and we have to find out the result in terms of the removal percentage of this IBP. And that has been put here at the extreme right column, right hand side of this column, where we have put this result based on the results we achieved on every experimentation, considering the single run of experimental matrix. Now this predicted versus actual IBP removal percentage per TCAB, and where you can see that these two are very close, very adjacent. Okay, and here it means necessarily that with this actual versus predicted data that are very close to each other, that are in good agreement with each other. Now, these are the results, so that you can consider here this adjournment dose. This is basically a 3D diagram, 3D plot, the surface plot and the contour plot. These are the plot of natures derived from this software, where we can see the nature of these different parameters and their influences on removal percentage. Okay, and here you can see that ibuprofen removal percentage is observed to vary more with the initial concentration, so that you can get from the surface plot and contour plot of both. And here one more thing is the removal versus temperature and initial concentration. You see, since it is a 3D plot, okay, and where these three different parameters that we are considering here, and where the two parameters that will be considered to vary subject to the percentage removal, that how much you are getting with respect to these two parameters in the process. So that are reflected in the surface plot and a contour plot. And here it is clear that the ibuprofen removal percentage is observed to vary more with temperature. Similarly, the time and initial concentrations, where we got that this is observed to vary more with initial concentration. Similarly, the temperature and adjournment, where we have seen that this is very much observed to vary with temperature. And here with adjournment dose and time, if the two other parameters apart from removal percentage that you are considering, and based on which here we can conclude also. So with adjournment dose, this is observed to vary more. And the last one is temperature and time, where this is with respect to temperature. I mean, just considering these two parameters based on the removals, which one is more influential? So that has been detected by this. Now, one of the study is isotherm study, where we have considered the languid and front-leg, which are the two isotherm studies, because this is very important thing, whether this adjorbent and adjorbate, whether this pair will be effective in attaining the equilibrium condition for the removal of these ions, or the expansion of these ions from the aqueous media at equilibrium conditions, and whether this process is technically substantiated by the results or not. So here the isotherms that have been considered, and where you can see that the languid isotherm with respect to the R-square value, languid isotherm that is best fitted with the data plotted and the data obtained from this experimentation. Second thing is the two different kinetics that we have considered, the first order and second order kinetics, and where we have checked that based on the R-square value, we have got that the pseudo second order kinetics is the best kinetics. That means this process follows well the second order, pseudo second order reaction kinetics. Thermodynamics, this kind of study that we generally do for the informations to get whether this process is spontaneous or not, and this process whether this is enthalpy driven, whether this is entropy driven. So that basically we have known here, and this delta H, this is indicating the negative, and this is exothermic process, and delta G, this is rising with increase in temperature, and it indicates that the lower temperature favoring adsorption process. Similarly, the entropy, this is recommending that process was decreasing randomly because with an increasing temperature, and it binds slowly with solvent. So entropy driven, enthalpy driven, or the delta G, whether this process is continuous or not, whether this is exothermic or endothermic. So this kind of thermodynamic informations we can get if we can study this thermodynamics on sorption process. Desorption study, this is very, very important, because these materials, solvent materials, what we have developed for the successive application, where we can check the decay in solvent activity for its further use in the repeated cycles for obtaining the effective removal. So whether these materials can be used, or the spent adsorbent materials can be reused further for the number of cycles for checking its adsorbent activity. So this desorption study that has been performed, and where you can see that even after 4 cycles, its removal percentage is 79.88. That means this is having a good repeatability in its application in the successive cycles. This is very important thing. This is very rare that the bioabsorbent preparation, how much the cost is attracted, and it is always informative for a successive application of this process along with the bioabsorbent in the commercial exploitation. So that is very important thing, and considering the different parameters associated with this bioabsorbent preparation, the cost that has been calculated, and here this is the 275.22 paisa. This is basically for 1 kg of this bioabsorbent material preparation will be required from these precursor materials what we consider. Now the conclusions. So these different parametric conditions that we have got and that are corroborated with the results we have achieved separately based on the manual optimization, and the reusability study that has been shown, where it has been shown that this is even after 4 cycles, its repeatability and its activity is really appreciable, but can be further recommended for its use in the cycles. And this biochar, this is highly capable of absorbing the ions. Now, these are the references that have used, and this is another area. Just I would like to draw your kind attention. This is another area, the domain of my research, where I might put my interest. That is biodiesel from microalgae and biodiesel from non-edible oil, where catalytic heterogeneous transesterification process that I generally consider for this, and the catalyst development in my laboratory, that is we basically handle, and nanocatalytic transesterification, that is also even in the recent program where we use the uncatalyzed transesterification process, and we successfully come up with a very good results. Anyway, so these contributions that are supported, well supported by the different funding agents, Department of Science and Technology, Department of Biotechnology, and this is my research collaborators. These are my research team members, my students. They have already got their PhD degree. They are working in different institutes. They are serving in different R&D institutions, academic institutions. They are basically my strength. Thank you. Thank you very much for your patience and giving me this opportunity. I am really thankful to the organizers for this such an opportunity to meet a number of good gatherings and a number of good participants over and around this country. Thank you very much. Am I audible, madam? Or
Sir?
yes. Yeah.
Yes,
My
sir.
presentation is over.
Now the session is open for question answer.
Yeah. Sure.
Over to you,
So
fine.
should I stop sharing these slides?
Yeah, please, sir.
Okay.
Yeah, good afternoon, sir.
Yes.
Question from Dr.
Good morning.
Sir. Can we use algae biomasses as alternative source of biochar?
I'm not getting your sound properly. Can you speak louder, please?
Can we use algae biomasses as alternative source of biochar?
Yes, of course. Algal biomass. Are you talking about the utilization of the algal biomasses as biochar materials for the treatment of wastewater?
Yes, sir.
Yeah. You see, this is a very good domain where this algal biomass that has been converted into the carbonized char, and the spent algal biomass that is used basically to be converted into this biochar, and this is a very good adsorbent, and we have checked also in our laboratory these kind of biochar materials developed from biomass for the substitute eradication of the different other pollutants, so that can highly be recommended for the conversion into biochar materials. But one thing is these parametric conditions that we have to check. Okay, I mean, at which particular temperature or time or other parametric factors it can be converted into a suitable biochar for its effective application, so that we have to optimize. Okay.
Sir has asked us other question about the specific parameters required for the consideration of biochar.
I cannot hear you properly.
Any specific parameters that are
Yeah, if you
required to
can.
consider as biochar?
Yes, please. Yeah.
Any specific parameters that are required to be considered as biochar?
Yeah, actually, you see, what I observe that temperature is very prominent factor, a very important parameter that we need to consider very seriously, because you see, if we use the suitable temperature, then it can help you to develop the micropores. It can enhance the surface area. Again, if we do not use the suitable temperature, suppose 550 degrees centigrade is the suitable temperature. Okay, but unknowingly, if you use 700 degrees centigrade or 800 degrees centigrade, then what will happen? The entire materials, it will be losing its pores and porous structures and surface active sites. Okay, so it will not be used as the materials for its effective application. So that temperature is very decisive factor. So you need to get the idea of proper temperature from the thermogravimetric analysis. If we just put this biomass in the TGA analyzer, then you can get the temperature at which temperature it will be suitably carbonized for biochar formation.
Fahim, any other questions? Yeah, Fahim. Can you hear me, Fahim?
Yes, ma'am.
Yeah.
Ma'am,
Yeah.
am I audible?
Yes.
Yeah, ma'am. There is another question from Dr. Madhavi, ma'am. What about the vegetable waste from households? Can it be explored as suitable biochar?
Yes. Am I audible to all of you?
Yes, sir.
Yes, sir.
Yeah. So you say the vegetable household waste, or this vegetable waste, what we used to get it from our house, okay, in our daily life.
Yes, sir.
So that vegetable waste, these are all lignocellulosic biomasses. Okay. So now, if these biomasses, definitely it will be converted into biochar. First of all, what we need to do, we need to get some idea about the fixed carbon content. Okay. So these materials, just 1 gram or 2 gram of the samples, if we can put it into the muffle furnace, and if this is undergone the proximate analysis, then you can get the information about the fixed carbon content, volatile matter content, moisture content, and ash content. So fixed carbon content is of the growing concern for the biosolvent development. Now this fixed carbon content, if we know it's really a good amount, okay, so definitely you can go ahead. And I'm telling you, this kind of vegetable waste possessing a good amount of lignocellulose, halocellulose, and homocellulose. Okay, this is having a capability of being converted into good biochar. Okay, I have already worked out it.
Oh. Thank you, sir. One more question.
Yeah.
Miss
Please.
Rajita and Sharat Chandrika in the YouTube,
Yeah.
they had asked, can ibuprofen be used for the treatment of psoriasis? If not, then what is the perfect cure for psoriasis?
Yes, please, pardon, please. Can ibuprofen?
Can ibuprofen be used for the treatment of psoriasis? If not, what is the best medicine for the cure of psoriasis?
You see, actually, this is not my part, because it can be better answered by any doctor. Actually, my concern is the treatment of wastewater containing the ibuprofen. That means the treatment of IBP laden wastewater. Okay. So this question, I think, better answered by the doctor, whether this is suitable for healing this psoriasis or not. Uh, how can I say that? It can be better prescribed by the doctor. Am I
Yeah,
right?
only ibuprofen is the part of treatment. That is not.
Yeah. My concern is the treatment of this IBP laden wastewater for its further consumption, where it will be completely contamination free, and how can effectively IBP be eradicated from this aqueous media okay, so that we can consume this water. Okay, so this is my major concern. Okay, so whether this IBP is suitable for healing this disease or not, so that can better be prescribed by the doctor. I am not the right person, I am telling you.
Yeah.
Yes, sir.
Yeah.
These
Really
are
very
the
informative
few
session, sir.
questions.
Yeah, please.
These were the few questions. By this, at the end of the session, I would like to thank everyone. A very good afternoon to respected dignitaries, principal, faculty, delegates of various colleges. Myself, Mohammad Fahimuddin, Assistant Professor, Department of Pharmacology, VIPER. It gives me immense pleasure, honor to propose the vote of thanks for the day 3 of the FDP and SDP session on recent advances in science and technology. I would like to thank Dr. Gopinath Haldar sir for delivering a startling lecture on biospore eradication of ibuprofen from contaminated aqueous media using activated biochar, which is a need of time that due to the contamination of water, many diseases are being spreading. So this was the need of time. Thank you, sir, for enlightening with your great research work on this aspect. And we hope to see you in such programs in future also. I would like to thank the management for trusting us and always embrace us to conduct such events. I thanks to Dr. Ramesh sir, Principal, VIPER, Chairman of this event, who always behind us and motivate us to do such programs. A special thanks to the Dr. O.N. Tiwari sir, the Principal Scientist ICAR, IARI, co-chairman of this FDP program, the backbone, I could say that he is the backbone of this FDP program for conducting such a great event. I would like to extend my thanks to Dr. K. Vanitha ma'am, HOD Pharmaceutics, VIPER, the convener of this event, and the coordinating and organizing team of VIPER for scheduling this and have made it happen. I would extend my thanks to Dr. Ms. Sandhya Reddy, Assistant Professor, who had gave a nice introduction of the speaker. Last but not the least, I would thank all the networking and supporting team who had played a major role to make this event a great success. Without them, this would not have been possible. I would thank all the faculty, delegates, and students of VIPER and other organizations who had participated across this India for making this event a great successful. Hoping to see you all in tomorrow's session. With more zeal and enthusiasm, I would like to take a bid by saying thanks and have a great day. Thank you.
Thank you. Thank you, sir. Thank you very much.
Thank you. So should I leave now?
Yes, sir.
Yeah, thank you.
Thank you. Thank you, everyone.